At its heart, computational imaging is about the mathematical structure of visual information. How do we use math to describe the physical world? Now, admit, we've been through a lot of discussion about coherence fields the last several episodes, and sometimes that may feel like a bit of a slog. But out of that theory, eventually some stunningly beautiful mathematics and physical insight may emerge, and that's what I hope you find in today's episode. Today's episode is about the application of the ambiguity function to description of the coherence function in the focal plane of an imaging system. This idea of using the ambiguity function has been around for over half a century. Here's one of the stunning papers that brought it to the fore of discussion of frequency analysis in optical systems. This is a paper by Karl-Heinz Brenner, Adolf Lohmann, and Jose Ojeda Castaneda. Pictured here you see Professor Lohmann, who was one of the pioneers of Fourier optics, and Professor Ojeda Castaneda. Here's a picture from when he won an award from SPI in 2021. What you see at the upper right here is a picture of the ambiguity function for a one-dimensional aperture. And you see spatial frequency on this axis, and this axis is actually denoting defocus. And it turns out that the defocus transfer function that we talked about in our last episode can be written as a cross-section of this ambiguity function, as we'll see today. But more broadly, the ambiguity function allows us to define the transfer function for the mutual intensity in imaging systems. So let's explain how that works. Computational Imaging. Episode 51, the coherence transfer function. We've seen a lot of this kind of transformation in this course, where we have some field distribution over here on the left that's going to transform into a field distribution over on the right. We talked about diffraction with coherent fields. We've talked about transformations of the input cross-spectral density to the output cross-spectral density. And in this chapter, we've been interested in focal transformations, where we have a lens that's going to form an image of the remote source in the measurement plane. Now, the image that we normally think of would be, an intensity image, the radiance image incident on a sensor, and that's what normally a sensor would measure. But as we'll talk about in the next set of episodes, the irradiance in the focal plane is not a complete descriptor of the state of the field and doesn't capture all the information available about the remote source. Today, we're going to talk about the transformation from a remote incoherent source to the cross-spectral density or mutual intensity at the focal plane. Normally, we'd write that transformation as shown here. So this is the cross-spectral density in the focal plane. This is the two-dimensional, we've assumed here, power spectral density of the remote object, and we have an impulse response. Now, the impulse response here is the coherent impulse response in each of the output variables operating on the incoherent input field. Now, because the field is incoherent, the phase modulation that we would have in the coherent impulse response in the object plane that we previously used for aperture synthesis in tachographic imaging goes away, because basically the two variables in the input plane that would have phase modulation on this object plane, they would have phase modulation, have that phase canceled when we reduce to just an integral over one variable for the incoherent impulse response. We still have phase modulation in the output variables x1 and x2, but that phase modulation doesn't really have anything to do with the input source, and so we won't find that phase structure useful in analyzing the remote source. Okay, so this is the general problem. This impulse response here is the coherent impulse response, which would be the Fourier transform of the exit pupil, and this is the phase modulation that we would get from the phase curvature terms in the coherent impulse response. We've written it here in terms of the mutual intensity, but we're going to be dealing here with quasi-monochromatic fields, and it's kind of cumbersome to carry around this dependence on wavelength and temporal frequency. So we'll limit our discussion to the mutual intensity, which is the intensity at a single time incident, or the cross-spectral density, or the mutual coherence at a single time instance. But here we're going to assume that we have a quasi-monochromatic field, so we'll just drop the time dependence altogether. Now we'll change variables as well. Instead of this x1, x2, we'll use the x bar delta x variables, where x bar is x1 plus x2 over 2, and delta x is x1 minus x2. And in those variables, this transformation between the remote emittance of the source and the mutual intensity in the focal volume, or in the focal plane, takes this form. We'll neglect this phase front term out front because it's just a phase modulation in our mutual intensity that we could just take out by multiplying by its conjugate, since it only depends on the output variables. Here we've written the mutual intensity once again in these shifted variables x bar delta x, and we still have this phase term, but we'll drop the phase term by just assuming that we multiplied by its conjugate to get this j tilde. And then we've changed this term in the product of the coherent impulse responses into a single shift invariant impulse response that describes the transformation from the remote intensity to the focal volume's mutual intensity. Now the delta x, delta y is still here, so this j actually depends also on delta x, delta y, but I just hid it because the delta x, delta y you can think of as parameters of the impulse response, and within those parameters this transformation is shift invariant in the x bar variables. So we have a shift invariant transformation from the two-dimensional object intensity to what's actually a four-dimensional mutual intensity, but we've hidden the delta x variable. So in these mean variables, x bar, y bar, the transformation from the input intensity f of x to the mutual intensity j of x bar, y bar is a linear shift invariant transformation. That means that it has a transfer function. So we have this impulse response, h tilde here that we've written as the product of the coherent transfer functions in the x minus delta x and x plus delta x variables, but that whatever its form in terms of delta x, that's a shift invariant impulse response for this j tilde. And since it's shift invariant impulse response, it has a Fourier transform and it has a transfer function. So the delta x, delta y remain parameters in the transfer function. We've taken the Fourier transform of j of x bar, y bar with respect to x bar and y bar, and then because this is a convolution, this is actually like f of u and b. That's the spatial Fourier transform of the input intensity, and this is our transfer function. So describing the spatial frequency transfer at each value of delta x, delta y to the spatial spectrum of the mutual intensity in the image plane. Okay, that's super interesting. We're going to find it a super powerful thing to know that basically the transfer from the input irradiance to the mutual intensity in the focal volume is a linear shift invariant system with this transfer function. Now, this is more general than the transformation that we've had, very similar thing where for the intensity where we set delta x, delta y equal to 0. We have the same thing, except that was going to be basically the input spatial spectrum times, this h of u v for delta x equal to 0 and delta y equals 0. So this should be the same as the optical transfer function. Here we've just generalized that for the mutual intensity. What we'll find to be super powerful and interesting is that there's extra information in the mutual intensity. So the intensity, the irradiance, is not a complete descriptor of the field. And if we could find a way to measure the mutual intensity, even though the bandpass we find won't be increased, the information in the focal volume is actually greater if we could measure the mutual intensity than if we measured the intensity itself. Now, in understanding and analyzing this transfer function that we'll call this the coherence transfer function, it's helpful for us to know about this ambiguity function. So ambiguity dates back to work in the 1950s on radar. Basically, in a radar system, you send out a pulse and you measure how long it takes for that pulse to return, and you've got the range to the object. But if the object is moving, there could be a frequency shift in the return pulse. So you get this F here describes a Doppler shift in the frequency of the return pulse. So it's not just delayed, it could also have some frequency modulation on it. If you wanted to measure that frequency modulation, you'd like the pulse to be long, which would allow you, a time or in Fourier space to measure the Doppler shift. But if you make the pulse longer, then you'll get less range resolution. So there's this trade-off between the Doppler frequency resolution and the range resolution, which leads to this function being called the ambiguity function. None of that is central to our discussion today, except for the fact that we're interested in transformations of this general form, the Fourier transform of a function shifted relative to itself, which is mathematically what we'll call the ambiguity function. Here's the Wikipedia page where you could go read all about applications of the ambiguity function. And of course, this is basically a kind of space-time, space frequency transform that occurs all over the place in Fourier optics. And so it is an interesting function just mathematically in a variety of contexts. On the Wikipedia page, there's a plot of the one-dimensional the ambiguity function for a one-dimensional function. So this is a two-dimensional, a surface plot of the same thing that I showed in the introduction today. This is a square pulse, and so its convolution with respect to itself is what's here on the zero Doppler axis, where the frequency, you're just integrating the convolution of the pulse with respect to itself. And as you go off, you're taking the Fourier transform of the shifted pulse, and you see these kind of fringe modulations along the Doppler axis that would be the same as what we saw in this density plot that was on the introductory slide. The ambiguity function arises in all sorts of contexts in optical systems, but today we're interested not in the ambiguity of the field, but in the ambiguity of the pupil function, which we'll find is very useful for describing this coherence transfer function. So this is our definition of the ambiguity of the pupil. We have the pupil shifted with respect to itself, and then we have the phase modulation as a function of frequency. So we get a four-dimensional ambiguity function for the pupil. So this functional form we've seen before. If we go back to episode 50, where we talked about the defocus transfer function, we've seen that the optical transfer function basically is the autocorrelation of the pupil with itself. If we add this phase modulation either from aberration or from defocus, we get a term that modulates the phase as we integrate over the shift, which is essentially similar to the ambiguity function. In fact, what we find is that this defocus transfer function is the ambiguity function with the appropriate variable substituted in. So here it's a function of spatial frequency in the transfer function and the defocus. So it's a three-dimensional defocus transfer function, and the defocus enters into these two spatial variables or frequency variables in the ambiguity function. But the defocus transfer function can be thought of as this cross section through the ambiguity function of the pupil. Okay, so that's just a powerful thing to understand as you go and analyze what the effect of aberration or defocus on a system. You could calculate the defocus of a pupil and understand its impact visually. But today we're interested in a different interpretation of the ambiguity function of the pupil. And for that, we're going to rely on a special Fourier relationship of ambiguity functions. So this is a definition of the ambiguity function of the function f of t here. So the function in one dimension shifted with respect to itself, and then having this frequency term that we also integrate over. If we went and substituted for f its Fourier transform, so we'd have f hat of u, and then e to the I 2 pi ut. Here, the Fourier transform would also have a frequency modulation term because of this shift, which would be like e to the I 2 pi u tau over 2. And then if this were substituting the Fourier transform here, we would have the integral of this over u would be equal to the function as a function of time. Now we could do that for both f and f star here. So we'd have a u1 and a u2. Once we substitute the Fourier transform, we could integrate over t, And so these f terms would be functions of frequency. Wouldn't depend on t. We have a bunch of exponentials in t. We'd get a delta function with the different relating the output frequency nu here to these internal frequencies u and let's say v for this term. So that delta function would allow us to integrate over one of the frequencies, and so we'd get an integral that would be the two Fourier transform terms with respect to itself with some kind of phase modulation. If we analyze that, what it turns out to be that there's a special relationship between the ambiguity function of a function f and the ambiguity function of its Fourier transform. That basically, you just shift the variables as shown here. Shift nu for t and t for nu, and you've got a relationship between the ambiguity function of an arbitrary function and the ambiguity function of its Fourier transform. So lots of very interesting math, but how does it come into play for us? Well, we're interested in the mutual intensity function, which has this impulse response, but this impulse response is the product of the coherent impulse response shifted by this delta x, delta y. So if we take the Fourier transform of this function, functionally, the Fourier transform of this shifted function with respect to delta x is the ambiguity function of the impulse response. So the ambiguity function of this impulse response h. But we know the ambiguity function of the impulse, or the impulse response is the Fourier transform of the pupil function. So by the relationship that we just saw, the ambiguity function of the impulse response is related to the ambiguity function of the pupil function. And that's what we see here, that the ambiguity function of the impulse response, written here as a function of delta x and spatial frequency, is equal to the ambiguity function of the pupil function with the variables shifted as shown in the relationship that we had a second ago. So the coherent transfer function is the ambiguity function of the pupil evaluated with spatial variables lambda di times u, and then frequency variables which would go proportional to delta x over lambda di. So the end result is that this coherence transfer function, the transfer function describing the mutual intensity in the focal volume, is related to the ambiguity function of the pupil as shown here. So this again is Fourier transform with respect to the mean position where we would measure the mutual intensity. So Fourier transform with respect to x bar, these are spatial frequencies with respect to x bar, and delta x and delta y are here as parameters. So this is a way for us to, given an input object distribution, to get the mutual intensity that we would have at the output. Let's look at the characteristics of what this ambiguity function looks like. If we had a one-dimensional aperture, again, this is the same plot that we've seen two different times before in this episode, but now we can write this in terms of this delta x and u. So this axis is spatial frequency in the output plane. And here we're looking at just at the positive quadrant of the spatial frequency and delta x coordinates. This is a one-dimensional aperture, so the optical transfer function goes like 1 minus the magnitude of the spatial frequency. And the maximum spatial frequency here is 1. That corresponds, in terms of this lambda over di units we're using, to a maximum spatial frequency 1 over lambda f number, basically. Okay, again, this is the maximum spatial frequency you have for a incoherent imaging system, and this axis for delta x equal to 0 corresponds to the standard optical transfer function that we have for irradiance. But as we increase delta x, we have a different optical transfer function. Now the envelope stays the same. No matter what delta x we have, the envelope is going to be this 1 minus magnitude u, the same optical transfer function we have. So we don't get a higher bandpass there. No matter what value of delta x we measure, no spatial frequencies greater than 1 over lambda f number are available for measurement in the output plane. But the relative value of different spatial frequencies changes as a function of delta x. And so by making measurements of the mutual intensity in these for different values of delta x, we have the possibility of changing the relative signal-to-noise ratio, which we measure different frequencies, or of measuring features of object space that are not readily observable by measuring the irradiance alone. Moving to a two-dimensional aperture, we can calculate the ambiguity of the pupil as shown functionally here by thinking of it that we have the pupil function, we're going to shift it by some amount, and then we take the Fourier transform of the overlap region of the shifted pupils. So if we evaluate this for a certain shift and at a certain frequency, that would be the Fourier transform of this overlap region corresponding to that shift. Now, when we're looking at this, we've changed the units so that the spatial frequency is in the x unit here, and the frequency that we have in the ambiguity function is represented by the delta x, the shift. So we would look at the pupil in the frequency space, the UV space, and look at a certain shift of the pupil, and then along the delta x dimension, we take the Fourier transform of this overlap region. If we could do that numerically, we get plots that look like this. So for delta x equal to 0, the transfer function is the same as the incoherent transfer function. So we get this envelope here that's the integral of the autocorrelation of the circle with itself. And then as we increase delta x, we find something very similar to the kind of ambiguity function we had for one-dimensional aperture, that we start to see oscillations along the spatial frequency axis, and the overall transfer function drops, although it drops much more rapidly at high frequencies than it does, or at low frequencies, drops much more rapidly at low frequencies than it does at high frequencies. So we have an increased relative response at high frequencies relative to low frequencies as a function of delta x. So this, again, as I said, I find to be astoundingly beautiful mathematically as a description of the what mutual intensity we get in the focal volume of a lens. The important thing to understand here is, again, we're imaging a remote incoherent object. So the field is incoherent at the object, but because the lens is a low-pass filtering system, it induces coherence in the focal plane. So at the focal plane, the field is not incoherent, and so there may be information in the mutual intensity that is not present in the irradiance. So measuring simply the focal irradiance is not fully predictive of the field itself, and if we find ways to extract information from the mutual intensity in the focal plane, we may get information that's not readily possible by measuring conventional images. We'll expand on this topic next time by considering the difference between the irradiance in the focal volume and the mutual intensity, and we'll discuss modal strategies for extracting some of the information from mutual intensity that's not readily measurable from the intensity itself. So we'll see you next time.